Hello, my name is Anna Petrasova, and I'm a research software engineer here at the Center for Geospatial Analytics. And disclaimer, I'm also GRASS maintainer and on the project steering committee. So with that, I would like to introduce you to the work I and my colleagues have been doing here at the center. One of the focus areas of the center is forecasting land change. And so one of the models we have been developing is future urban regional environment simulation. And I think what sets this model apart from the other urban growth models is that it's stochastic, and it realistically captures the spatial structure of development, which can be critical for a lot of environmental processes. And also it's very flexible in terms of what kind of inputs you can use to kind of match the dynamics of the actual landscape. And we took the original prototype of the model and implemented it as a GRASS add-on toolset, R.Futures. And there was a couple of reasons and a lot of benefits coming with that. So GRASS has module architecture. You can have tools in C and Python, which was kind of exactly what we wanted, where the simulation needed to be in C or similar fast running language. And then we had a lot of pre-processing tools that access a lot of geospatial functionality. And so that was very useful. Also, there's a lot of convenience features. You get very easily command line interface, graphical user interface. So it's nice for distributing this to the users. It provided us with the infrastructure for documentation, for distribution of the binaries, and it's maintained by us, but also the broader community. Another important part of it is that we are able to take advantage of a lot of the efficient libraries and parallelized tools. These are some of the parallelized tools. Some of them we used for some of the pre-processing. And so what we decided to do is we ran the simulation previously in some kind of smaller scale, but we decided to take up the challenge and scale it to the United States. And so we took advantage of the NC State HPC cluster. And in terms of computation, we computed it at 30 meters, which meant about 16 billion cells. And the model is stochastic, so we need to compute a lot of stochastic runs, 50 stochastic runs, and we were projecting over 80 years annually. In terms of the parallelization, we decided to split the simulation by states, and that was distributed on the HPC across multiple nodes. And a lot of the pre-processing, post-processing steps, we utilize the kind of embedded parallelization in the tools themselves that use OpenMP. And this is kind of the result, pretty picture. So this is showing one of the stochastic runs. And obviously we derived also probability and things that are useful for the end user. So the data is published. And with this, I would like to thank to my colleagues, especially Georgina, the Center for the support, and GRASS community, other GRASS developers, mainly Vasek, and I will thank myself. Okay.